Cool. Hello, everyone. It's nice to be back, and thank you, everyone, for sticking all the way to the end. And don't you worry, because today I'm going to talk about two notoriously lightweight subjects, non-blocking concurrency and purely functional programming. So nothing to be afraid of there. So I came here last year, and I gave a talk on shared state in pure FP. And in that talk, I was explaining how it's possible through I/O to get both referential transparency and concurrent mutation. And it's not only possible, it's actually desirable, because you get a very nice model for controlling which state is shared and which one is isolated, just by passing things to functions. And then you have this very nice property that the regions of sharing are the same as your call graph. And then towards the end of the talk, I reached a conclusion saying, there's a lot of business logic that you can capture in tagless final abstraction, and then they're going to be backed by concurrent abstractions built on this stuff. And then I left it off as the next step. So this talk is the next step. It's the natural successor to that one. And I'm going to be talking about a concurrency scheme built on top of these two primitives, ref and deferred, and exploring how they form this nice composable base to build all sorts of concurrent abstractions, from simple counters to concurrent finite state machines. So let's get straight into it. My name is Fabio. I'm a principal engineer for Over Energy in London, and also an open source developer, mostly as a core maintainer and contributor to Cat's Effect and FS2. And I want to start with a bit of history. So I see this API evolved over time. So in FS2, all the way back in 0.9, we had this thing called ref, which is actually very different to what we call ref today. It was backed by a custom implementation of actor, very low level, and this ref could do all sorts of things. You can set and get state, you could modify state, you could wait on things, you could handle errors. It was sort of very complex. And then in 0.10, I redesigned this scheme to this new scheme built by these two primitives, ref and what are called promise at the time, which is essentially what we have today. And then we migrated it to Cat's Effect in 1.0 and kind of renamed promise to deferred just to avoid confusion with the standard library. And so that's where we are now. So let's get started by talking about ref, which I kind of touched in the previous talk, but now I want to explore the API a bit more. So what's a ref? A ref is a purely functional mutable reference, and we know that this is not an oxymoron. It's a referentially transparent mutable reference. There's no problem with that at all. It's concurrent and lock-free. We're going to see what this means. And the key thing about ref, the ref always contains a value. So you cannot have an empty ref. There's no concept of empty ref. And again, this is not a quirk. It's a fundamental reason for this choice. And at the core, it's just I/O plus atomic reference. We're going to talk about atomic reference a bit. It's a low-level Java primitive. So let's start with the minimal API. The first thing I want to point out, too, is the constructor. You see, you need to pass a value to the constructor, because the ref cannot be empty. So to build one, you need to pass the initial value. And it returns I/O. So yeah, it's created by giving an initial value, and every operation is wrapped in I/O, which gives us purity, including creation. This is the crucial bit of my previous talk. And the other thing is that A is an immutable structure. So ref is a way of giving purely functional mutation to an immutable structure. So you have an immutable list, you want to mutate it concurrently, you do it with putting that in a ref. And finally, the real version is not specialized on I/O, but it's polymorphic in F from Cat's Effect. So you can use it with Monix or whatever else you want. So, sorry, the API I showed, it's just got get and set, which I think are kind of self-describing. You get the value, and you set it to a new value. So let's see if this API is enough for us to do what we want to do. So imagine we're kind of building some sort of reporting or tracing or logging thing. And we have this report method, which takes the trace, which is just a ref with a list of string. The list of string is just a logging trace and a new message. And I want to append the new message to this list. So I'm going to call traceGet, which returns me an IO of list of string, and flat map it. And then I'm going to just do traceSet, appending the new message I have as an input to the log, to the trace. And a call site, I'm going to create this ref, and then I have two calls to report, but they are started with this method called start. So start, what it does is sort of spawns a fiber. So what's happening is that these two report calls are actually running concurrently. So if you've done any sort of concurrency, you might be able to see a problem straight away here. We can lose updates. How do we do that? So imagine that one gets and then two gets, right? And they have the same list. And then one sets and then two sets, essentially overriding the update that one had. So we can lose updates. So as it turns out, get and set is not enough when you have concurrency. And it's also another reiteration of the point I was making last year, that the state monad is not enough, because in the state monad, modification is exactly get and then set. But when concurrency is involved, get and then set are obviously not enough. So what we need an update method. And again, this update is not going to be the composition of get and set. It has to be something else, because we need to do it atomically. And once we do have that update method, obviously it just takes a function from the old state to the new state. Our report just changes to this. We are going to call update, and update takes a function that will take the old state, which is in this case is the list of strings, and just append the message to the list of string. And this is safe. So ref supports concurrent state. So it's built so that this is safe. And in the slide or two, we are actually also going to look at how that works. Okay, so the next question is update enough? Is update all we need for this interface? So let's look at this other example. Imagine we're modeling some sort of race. So we have a sprinter with a name, and we're passing in this finish line, which is a ref of ints. So the idea is that the finish line tracks our arrival in this race. So and then this sprinter means, it's the method you call when you're done, when you've arrived. So the first thing you do is you call update to increase the arrival. Like maybe you're third, the state of finish line is 2, so you do that atomic update, and now the state is 3. So it's fine, update is atomic. But then we need to know which ones are we. So what was our own arrival. So we just call get on the ref that we just updated. And then we just print line to say, well, I've arrived at position, say, 3. And the way we're going to run these things, again, we're going to create this ref starting at 0. And then I'm going to put these 3 sprinters in a list, and I'm going to call pass sequence. It's not important to understand what it does in detail, but basically it's going to start all these things concurrently and only return when they've all arrived. Now the problem with this is that you can actually get a wrong result. So let's see why. Let's say I update the ref. So we started at 2. I'm third. I update the ref. That's atomic. So now the ref is 3. But before I can get, someone else updates it, and now the ref is 4. And then I get, and I'm 4, and they're also 4. So you get this wrong result straight away. And the problem is that you not only need to update, you also need to return a result based on that update. And this also needs to be atomic, which in this case it isn't. We're doing update as a thing and then get as another thing. Because it turns out we need a slightly different method called modify. So modify looks a bit like update. It takes an A to A, but instead of just returning the A, we also want to return a B. And the b is arbitrary. We get to decide in the function how to produce the b from the state, from the A. And then modify, it doesn't return an IO of unit, it returns an IO of that b that we just computed. So what it's going to do is going to atomically set the new state, produce the result, and give you back that result. And now, in the case of the sprinter, we just call modify on finish line instead, saying, well, the new state is going to be the old state plus 1, and my arrival is also the old state plus 1. And this is atomic, so that can never happen that someone sort of messes up with the ordering again. And so again, this problem is solved. And also we can see that update is actually just a special case of modify where b is unit. So modify can be written as modify, but the state is just unit, and so we return unit. So we just call update where we don't care about computing some sort of result. We just care about the next state. Okay, so what are the limitations of ref? It might seem that we're not that far from being able to do this instead. So note that the f there is a bit different because it's not just A to A, it's A to IO of A. So it's basically saying, I want to get the old state and then do some effects, and based on the result of that effect, compute the new state. And we cannot do this with ref. It's not possible. So why is it not possible? Let's have a look at how modify works and how update works. Modify is the same, we're just threading an extra thing. So to be able to understand this, we need to talk a bit about atomic reference. So atomic reference is a Java primitive to do lock-free programming. This is sort of convoluted a bit, but it's actually the simplest thing you can do when you're talking about this sort of concurrency. And it's called a CAS loop, a compare and swap loop. So the key idea is that atomic reference contains some immutable data. And I'm going to get that this atomic reference, by the way, is a side effectful thing. That's why I'm wrapping the whole thing in IO. It's from Java. There's no monads or nothing there. It's just Java code. So I'm going to get the current state on the atomic reference with get, and then I'm going to return the new state just by applying the f. And so far, so good. You know, everything is immutable. I got a copy. I produce another thing. But now I need to actually do the update, which is done with this compare and set method. So the idea behind this is that you only want to set the actual state of the atomic reference to your state if nothing has changed since the time you read. Because if nothing has changed, then you know we're safe. But if in the meantime, if in the time between you getting and modifying and then resetting, someone else has modified the atomic reference, then you don't want to do that. And what do you want to do? Well, you just retry the whole thing. So you just call loop, and it goes back into gets the new state, modifies it, and then does this compare and set. So the way compare and set works is basically you need to pass, you call it on the atomic reference, you pass the old state, which is the state you want to compare. So you're saying, is the state of the atomic reference the same as old state? And if it is, set it to new state. And return true. So this compare and set is atomic, and this is a JVM thing, so it boils down to kind of processor instructions. So there are no locks there. It's a primitive instruction. But then, what's the problem with this nope method? So note how you don't know how many times loop is going to run, because it depends on how many fibers are trying to set the same ref. If it's only one, it's going to run one. If it's two, it might run one. It might run two. It might run 3 times if they get very unlucky. And if it's a lot, it might run, I don't know, 100 times. And until we're just setting a new thing, so just a new value, it's fine. It doesn't matter that we recompute f a non-deterministic amount of times. It's just +1 on an integer. But if f affects, it means that we might be running an effect a non-deterministic amount of time, which is obviously not what we want. So the problem with this is that it needs to retry f non-deterministically. If that f is like write to db, you definitely don't want to say, well, depending on the contention, I'm going to write once or twice or 4 times. So we just rule that kind of operation. And also means that if you cheat and just write f a to a and put side effects in there, you're on your own. Don't do that. But then why do we do it? Well, there's a couple of reasons. First of all, believe it or not, the first time I saw this, got introduced to wait-free and lock-free programming, I thought, oh my god, this is so wasteful, you're just retrying the whole thing. As it turns out, this is way faster than locking, because it's just a very, very fast primitive operation. It doesn't have to do all the complicated machinery to block a thread and do the whole context shift between threads. There's another reason, which is that this actually cannot deadlock. So if you do this with a lock would allow you to do effectful updates. But the problem with a lock, even if you write code correctly, you acquire the lock, and then your thread just doesn't get scheduled. Everything is stuck because you haven't released the lock. Whereas with this scheme, even in the worst case scenario where your thread never gets scheduled again, other things can make progress because they're just gonna, keep doing their compare and set on their own. So it's very performant and cannot deadlock. And that's ref. So we can basically modify some state and return a result, but we cannot do effects in modify. Okay, so let's talk about deferred now. So deferred is a way of encoding purely functional synchronization. So synchronization just means waiting for something to happen. And it's got very simple one-shot semantics. We're going to see what this means. And finally, it features semantic blocking. So what does semantic blocking mean? In short, it means that the fiber is waiting, but the underlying thread is free to run many other fibers. So the TLDR is that blocking a fiber is fine. If you're not satisfied with this answer, I have a massive talk on the fiber internals, which go into a great depth into how this works and a mental model for it and code to implement it. So but for the purpose of this talk, it just means that we're actually blocking a fiber, we're not blocking a thread. And because we have a lot of fibers, we can block them with no problems. Whereas if we would do actual thread blocking, then we might have problems because we don't have that many threads. So let's have a look at the API. And deferred is a very, very simple thing. So it starts empty, always. And then at some point, it will become full. And then once it's full, it will never be empty or change its value again. It's done. And that's what I mean by one shot. It's empty, and then it gets completed with a value, and that's it. And you see that the API kind of reflects it. You have apply, which creates a new empty deferred. They get in I/O, because we need to be pure, and this has got some shared state in its internals. Then you have get, and then you have complete. That takes a value you want to complete the deferred with. And again, the real version is polymorphic. I'm just, for the sake of shorter slides, I'm just putting I/O there. So but what's the behavior of get and complete? There's only two methods, so what do they do? So let's start with get. If you get on a full deferred, it will just immediately return the value. It would give you an I/O with the value there. So nothing strange. And we know that once the deferred is full, it will never change that value. And on an empty defer, it will semantically block until a value is available. So if you do a get on an empty defer, it's just going to block the fiber until someone else fills or completes that deferred with the value that you're waiting for. And then we actually support interruption in case effect. So if you want to interrupt it, you can. Typical case, you want to wait on a queue, but you want to time out and only wait for 10 seconds. If there's nothing, I'm just going to stop and do something else. You can interrupt this safely. And then complete. If you complete an empty deferred, it's going to fill the deferred with the value and just awake all the readers. And if you complete on a full deferred, it will just fail. It will fail with a fail I/O, that you can then handle error and do whatever. So very simple semantics. Okay, so let's have a look at an example of why you might want to use deferred. Using the simplest kind of deferred use case, it's gates. So imagine I've got this. I've got some sort of consumer that can read one message, but this consumer, it needs some setup before it can start. It doesn't matter what this is. You can think about a complicated network thing that needs to be initialized or do some handshake or whatever before it can read the message. And then I've got a producer which can write a single message and assume that they know how to communicate with each other already. But this producer also needs setup, and the setup is also slow. So let's see how we use it. So it's very simple. I'm going to just say I want to set up the consumer, and then read the message and print it. And on the producer side, I want to set up the producer and then write a message. So basically, we're just modeling a scenario where the producer is sending one message to the consumer, and the consumer prints it. Very simple. But because the setup is slow for both things, I'm actually going to run these two things concurrently. I don't want to set up the first one and wait, and then set up the second one and then do. I just want to do them concurrently. So the two setups are going to be happening concurrently, which is more convenient. Okay, but now we actually have an issue that the message can get lost. So why? So let's say that the producer is faster. So again, they've been started, so they're running concurrently. The producer is faster. It finishes its setup and it sends the message, whilst the consumer is still setting up, and the message is going to get lost. So, and assume there is no special buffer or anything like that. So we're just going to lose the message. So the obvious solution is to just do the setups sequentially, but then we kind of we're throwing the baby out with the bathwater, because now we have to wait for both to finish. So what we want to do instead is we start them concurrently, but we don't write until we know that the consumer setup is done. So we need some sort of way of waiting for a condition. And as it turns out, a deferred kind of does just that. So this is the simplest deferred, just a deferred of unit. It can only contain a thing which is a unit. So what I'm going to do, as a consumer, I'm going to set up myself. And once I'm done, I'm going to complete that deferred with unit. So signaling that I'm done. And as a producer, I'm going to set up, and then I'm going to call get on that deferred. I remember, get is only, if the deferred is empty, get is only going to continue once the deferred is full. So what happens is that if the consumer is faster, it's going to go do the setup, complete the thing, and the producer sets up, the unit is already there, so nothing happens, everything goes fine. And if the producer is faster, everything is still fine, because the producer is going to be fast, but then stop on that deferred.get. And it's not going to continue until the consumer has signaled that they're ready to go. And there you go. So you can still run most of the setup concurrently, but if it happens that the producer finishes a bit early, then you don't lose a message, because you introduce this happens before relationship with this deferred. Okay, but wait. What if the consumer setup fails? So this seems like all okay, it's fine, but what if there's a failure here after setup? Well, I/O is a monad error, and when you have a failure, you're going to short circuit, and so the deferred is never going to get completed. And because it's never going to get completed, this producer now is stuck forever on that done get. So this is not as bad as thread blocking, because the thread is still free, but it's still bad for logic. You're basically waiting forever. So as I said, we support interruption, so you can definitely say, well, I'm going to do done.get and timeout. And in many cases, that's actually what you want to do. You just want to time out and do something else. But I'll show you another technique. So instead of just returning, instead of having this gate be a deferred of unit, I'm just going to have it as a deferred of either throwable and unit. So I'm going to represent not only the possibility of success, but also of error. So now, when I'm waiting on that deferred to complete, I'm waiting for either a success in the setup of the consumer or an error. So I call setup, and then I attempt. So attempt kind of materializes all the errors, so that you don't short circuit anymore. Instead, you have this either that you can deal with. And then you complete with that either, which is either throwable or unit. We don't care about the consumer itself. And then on the setup, of the producer, I finish my setup, I do get, and now I have an IO of either throwable and unit, and I'm going to call rethrow. So what rethrow does is the opposite of attempt. If I have a left, I'm just going to fail it in IO. So this behavior basically means that if the consumer fails, the producer also fails immediately, rather than being stuck forever. And then you can do your error handling. But the point of this slide is not so much to describe this scenario, but rather to make the point, which I didn't make in writing, but I will make it now, that every time you introduce waiting, things get more complex immediately. Because now you need to worry about, oh, okay, what happens if I wait forever? What if two things are waiting on each other? So, and this is actually central to why this is designed this way. So waiting is essential, obviously, for concurrency, but it's also complex. Okay, so that's the end of the introduction. We can actually review the API. I am quite pleased because it fits on a slide. It feels like a good achievement. So you have ref. You create a ref. This is, by the way, this is the full API, all polymorphic and all. So I have abstracted IO away. You can create a ref, giving it an A. You can get or set on the ref, and you can have them modify that atomically is going to update the state and give you value. And then you have this deferred, very simple semantics, empty or full, and that's it. And then get is going to wait on an empty, and complete is going to wake all the waiters. Okay, at this point, I think maybe you see why these are little useful tools. You know, they seem to be useful, but it's not very clear how are these foundational. So I was saying, oh, you can build all sorts of things with this stuff, and they just seem very limited. So ref cannot do effectful modification, which is what we want to do most of the time. Imagine a cache, we want to get something and then modify the cache, and that get is going to be an HTTP call, and we can't do that with ref. And deferred, on the other hand, can only wait on a single thing, and then it's done. We can just throw it away. And that's weird, right? Because normally we want to wait on several things. Like you want to get on a queue, and every time the queue is empty, you want to wait. And that's not just a single condition, it's several. So the question is, first of all, how do you then do what you need to do with this? And second, why do you do it this way? Are there any advantages to this model versus locks or any other thing that you might be familiar with, like if you know Haskell, like something like mbar, for example? So the key idea of this scheme is to separate concurrent state from synchronization. And then we are going to design the simplest primitive for these things, and then we're going to assemble them compositionally. And as is often the case, when you do it this way, compositionality helps you out in ways that you didn't envision. And actually, towards the end, I'm going to show you an advantage of this scheme, which I hadn't thought about when I designed it. It's something that just happened. I cannot reason about it after the fact and say, oh, okay, this is why it's working well for that problem, because of this separation. But for now, let's discuss about why I thought this is going to be useful. So again, the key idea is that ref, I just want to change a value atomically. That's the simplest possible way of concurrent state. I'm just going to change a simple value atomically. And the simple possible thing for synchronization is I just want to wait for something to happen. These are the two key ideas. But then how do we build stuff, and why do we build it this way? So note that ref cannot deadlock. So we know it cannot deadlock because there's no waiting involved. And then I'm going to use waiting only when needed. I want to minimize the amount of waiting because, as we've seen, waiting breeds complexity. And the way I'm going to introduce waiting is by putting deferred inside of refs. And the interesting thing here is that because so deferred is this unidirectional waiting. It can only be empty and then full, and that's it. It cannot become empty again. And if you've seen locks or Haskell mvar, an mvar can be empty and full and empty. You can always block in both directions. But because deferred has unidirectional waiting, if you want to wait on a new condition, the only way to do it is by creating a new deferred. And so you move your logic from the weighting to this function, because you are now modifying the ref to produce a new deferred instead. So you're moving the logic from this effectful world of waiting and locking and potential deadlock to a world of a simple function to the next state. And this is the reason why I think this is nice. In my experience using locks or mvar, if you only need one, that's fine. It's rarely the case that you only need one. As soon as you need 2 or 3, it gets very complicated. And the reason it's complicated is because the state space is huge. They can be empty, full, and then empty again, and then full again, and there's waiting in all directions. Whereas in this case, we can reason about the possible stages much more methodically. So it might not be easy at first, but we have a methodology to build these things. And in fact, I think there's one specific pattern which I found very useful, which is finite state machines. In particular, concurrent finite state machines. So I'm just going to give an informal introduction, no math. But basically, there's going to be a set of states, and then we're going to have concurrent inputs. So normally, you just say that a state machine takes a single input, but in this case, we are modeling things that can have multiple inputs concurrently. And then there are transitions between states on inputs. So on each input, there might be a transition from one state to the next state. And then finally, after a transition is done, I'm going to run an action. So that's what concurrent state machines are. Well, then let's look at this transition function then. So the transition function needs to take a state, and then return the next state, and also return an action to run once the transition is done. And if you look at modify from ref, it kind of fits that shape. You have A being equal to S, and then B equals f of C. And so if you then substitute in the output, you get an f of C, but we know that we can just flatten on that IO, on that f, whatever, and have the desired outcome. So the semantics of this is going to concurrently do the state transition, and the state transition is going to return an action, and the action is only run once the transition is successfully completed. Now, when you look at this, you might notice a resemblance to actors somehow. You know, there's this notion of internal state that you update, and then you do stuff after you update it. And in principle, it's true, but in practice, I find this to look very different and feel very different, and I think it's for 2 reasons. So first of all, there's this very different way of sharing state, which again is what I talked about last year, where you're not just going to not just going to be sending shared state all over the place, but you need to actually pass things around through function if you want things to be shared. So you can't just refer to a name; you need to have that reference passed into you. And the second big reason is because normally around these little abstractions, I'm going to have streams. And when you have streams, you can actually centralize behavior. What I mean by this is often with the actor model, you need to split your logic in several different places and things. You have an actor that pulls something, and then it's going to send a message to another actor, which is going to do something else. And whereas with streams, you can have a single stream saying, you know, this stream is going to wake up every 3 seconds and do this. So what happens is that you just get this one expression that describes your whole behavior. And streams can also, you know, do concurrency, so you can have 2 streams at the same time, and they're all in the same place. And more importantly, they're modular because they're referentially transparent, so you can replace things and still know what's going on. Okay, so enough about principles. Let's go through a concrete example. So before we get into the details, it's not really important the sort of semantics I've chosen for this. So this is a problem that's actually pretty interesting. There's a lot of possible semantics. The point is not so much to describe the semantics I've chosen, those are fine, but to show you a methodology for how to design this thing. So what I want to build is a little memoized cached value. So basically, I want to say that there's an effectful task, this FA, and I want to run it when someone calls get. But this get is called concurrently. So if someone else is calling get, and the task is already executing, I don't want to start another one. I want to reuse the result of that. So doing some memorization. And after this task is done, if you call get, you just get the result. You don't rerun the thing again. And I also want to then have an API for expiration. Saying, if you want to expire the value, I'm just going to call expire, and when you call get the next time, then it's going to restart your thing. And this is actually pretty useful. I have variations of this all over the place in my application code. You can put these ones in maps and build caches, or you can memorize simple things. And there's even a more complex version of this in Cat's Effect proper called memorize. So we said that the way we want to deal with this is through a state machine. So we need to describe the state space. And I'm going to describe it as simple ADT. So the first state this can be in is when there's already a value. So it's just going to be a case class value with a V inside, with an A inside, that's the value. And then there's another state it could possibly be in, which is no value. This means either no one is called get, or someone is called expire and no one else is called get, so there's no value in there, it's empty. Or it's actually in the process of updating. And when it's in the process of updating, it means that there's some waiting involved, because the next call to get needs to wait for that thing to finish. And because there's some waiting, I just put a defer in there. And because the FA might fail, I put the either throwable of A. OK, so the whole thing kind of fits into this. We're going to go through it slowly and see what's going on. So let's start from get. I'm going to create a deferred, because I might need it for the update. And then I call the modify on. So let's start from here, actually. So I'm going to create my ref. And I need to pass an initial value. And the initial value of that state machine is no value. Nothing has happened yet. And then I'm just going to create a cached, implementing those two methods. Then I create a defer, because I might need it. And then I call modify on the state. So remember, modify is when you pass the transition function, defining how the state machine should evolve. And now we have three cases. If the state machine is in the value state, it means a value is already there. So the next state is not going to change. It's still going to be value. And my return action to run when the transition is done is just calling pure on the value. And then, if it's updating, it means that updating contains a deferred, and the state is still updating, and I'm just going to wait on that deferred with this get call. So if something is in updated state and another thing calls get, they're not going to start the program twice. They're just going to wait on the one that's already running. And then the interesting one, which is no value, if there's no value, I change the state to updating. Remember, this is atomic. So if the first call to get that gets no value is going to change the state to updating. And then it's going to call this fetch function, which you're going to see. And what the fetch function does is going to basically start the task and then put the result in the right place. So let's have a look at it. We need to pass the condition to fetch. So this is the defer that other tasks might be waiting on. I run FA, attempting, so that I don't show signal errors. And then I'm going to set the state. And if FA failed, I'm going to set it to if I failed, I'm just going to set the state to no value. And that means that, and again, there's possible choices to do this. But this is it's the most obvious, right? The thing is failed, so I'm going to set it to no value. And if the thing succeeded, I'm going to set it to value. So all subsequent calls to get are going to get the right result. It's either empty, because the thing couldn't update, couldn't succeed, or it's full. And finally, I need to account for the case where someone has called get whilst I was in progress. And if you look at this, it means that they're all waiting on this deferred. See, this get here. So I need to complete it with their result. And then there's going to be a retro. So if I'm waiting and you fail, I'm going to fail as well. And finally, expire, which is very simple. If it's value, I just change it to no value. If it's no value, I'm just going to change it to no value. And for updating, you have a few choices. The one I chose here is that if you're expiring something that's already being updated, we ignore the expiration. It means that someone else has already done it. Again, there's a million possible ways of doing this. This is just for the sake of the example. And that's it. So we've done it. Concurrency, non-blocking, purely functional, done. Except there is this thing called interruption. So interruption, very shortly, just means that you want to stop something from doing something because you want, classical example, timeout, after 5 seconds, don't do it anymore. The problem is that this is very complex. And this complexity, I think, is fundamental because it conflicts with resource safety. So the ability to always close a resource. And think about it this way. Interruption means that you tell someone, no matter what you're doing, stop. And resource safety, it means that you're replying, no matter how important the thing you want me to stop doing, no matter how important you think your command is, I need to do something, I need to close this resource. So this is like fundamental trade-off. And the interface we have right now is quite complex. We have a better version probably coming in Cas Effect 3, but I want to show you, a bit rushing, I want to show you how to do it now and possibly how it's going to look like in the future. So first of all, you need to understand all these different semantics of these different combinators. The only one we're going to talk about is on cancel. So on cancel just runs on one action when cancellation happens. And the action itself is not cancelable. So it's just a way of saying, no matter what happens, if I get cancelled, run this. And then the key idea is that instead of thinking, okay, when did interruption happen, you're just going to restore the state. So the important thing is that you never leave things in an inconsistent state. And as it turns out, actually separating state and waiting helps, because you only want to restore state, and you only want to interrupt waiting. That never makes sense to interrupt a very simple Cas loop. It's only when you're waiting. So this is the thing I was mentioning in the beginning. I didn't think about this because at the time we didn't have interaction, but as it turns out, it helps with that. So let's have a look at how this thing can be interrupted. So it can be interrupted on any flat map and on any sort of semantic blocking call like get, but it cannot be interrupted on this modify, because that's just a chunk of imperative code. So if it's interrupted here, that's fine. I don't just, I want to stop you from getting a value, you don't get the value, no problem. If it's interrupted here, that's also fine. It means that I'm waiting for someone else to complete, and someone stops me. Okay, I stop, nothing's changed. But if it gets interrupted in fetch, now there's a problem, because I've interrupted the only person, the only thing that can fulfill that deferred. So the other things that are waiting are now going to get stuck forever because this thing got interrupted. And if you go inside fetch, we actually have a million places where this can be interrupted. It can be interrupted before doing this FA, so nothing is executed. It can be interrupted after doing it, before setting the state properly, or it can be interrupted after setting the state, but before completing that deferred. So trying to reason about where that happened, it's not possible because it can happen at any time. And then, expire is fine. There's just an update, so nothing to interrupt there. So what we need to do is go on that fetch and restore the state in a way that never leaves things in an inconsistent state. And actually, the code to do this is actually very small. It's dense, but it's small. So what I want to say that on cancel, I'm going to do another modifier on the state and try and reconcile any problems. So if I modify and there's a value v, it means that the state is in a proper state. It means that it got interrupted here. He managed to do the thing, complete the state, but never might or might not have completed this deferred. So what I want to do, I want to complete the deferred in case it was interrupted here, but also attempt it, because in case it was interrupted here, the deferred is already full, so I want to attempt to avoid that problem when you try and complete something that's already full. So I kind of need to think about the possible scenarios and do an action that's going to work in all possible scenarios. And then, with no value or updating, is the same thing. It means that it didn't succeed correctly, so I want to set the state to no value. And then I want to complete the deferred in case it didn't manage to do it here with an error, and there might be, I got interrupted, deal with it. But if it did manage, then I'm going to fail here, so I want to attempt. So again, this is fairly complex, but there's still a methodology to it. So you look at the state and try to restore it to this sane state that isn't corrupted. However, since it's pretty complex, you generally tend to need some experience to do this. We're thinking about a different API to address this. So this is coming in Casafet3. I cannot promise it's going to look this way. It's just an idea for now. Basically, the issue is that we don't know where this interruption is going to hit. Whereas the only thing we care to interrupt is FA. That's a long-running task. These other things, we don't care about interrupting them, but because we can, we have to do all this sort of, reconciliation. So in 3.0, it might look a bit like this. Because action is the thing that we care about, we're going to say FA, attempt, and then on cancellation, just set the state to no value and complete any deferred with an error, which is what we want to do. And then I'm going to put all this thing in an uncancelable section, which means that cancellation cannot happen anywhere, except I want to cancel the action, so I'm going to put this cancelable thing here. So I have this notion of cancelable and uncancelable regions, where inside the uncancelable, so in the normal scenario, interruption can happen anywhere. Inside uncancelable, interruption can only happen when I say it can in cancelable. And so now I know that if interaction happens here, I know how to deal with it. And if it doesn't happen here, it's not going to happen at all. And this is how we think about dealing with it. There's still a few questions about how to implement this thing, how to put it in a type class. So there's some work to do. And Casafet3 is still like a few months away. But even if you use the old model, this separation of state and synchronization still helps you dealing with this issue. And don't think that because you've never seen it, it doesn't happen in other schemes. With locks, it also happens. It's just way more complex, and you deadlock the whole thing. So I think this complexity is not incidental. It's fundamental, because there's this conflict between interruption and resource safety. I want to do something, and I want you to stop doing something. And that's it. So this is ref and deferred. And you can use it to build all sorts of things. I've used it, and not just for libraries, by the way. I've used it in applications to do caches, sliding windows, all sorts of things. And depending on what you do, you might not need it at all, or you might need it all the time. But hopefully now you have a set of tools that can help you reason about this very complex problem a bit more easily. Thank you very much.
Questions? Come on. This is your last chance. Great.
Thanks for the talk. So I was wondering, why cannot we make ref modify cancelable? Because there's a loop.
You can, but it's not a good idea, so we did it.
Okay.
So the reason we can't do it right now is because the way it's implemented. Where is it? It's just an IO.apply. So it takes a chunk of JVM code and just executes that. So you cannot really interrupt it. There's a few caveats, but on the JVM in general, you can't interrupt a chunk of code like that. You could if you said, just wrap this and do a loop in IO with flat map, but you don't want to do it. We have already enough interruption as it is. You want to keep your sanity. And again, it's about finding the balance. If you have too little, you might complain because you want to block something that's right into the database once you type it out, and it's not blocking, and it's not stopping. And if you have too much, then you want to finalize something, and you get interrupted. So again, that's that problem there.
Right. Okay. Thanks.
Yeah, and just a final note, even though you might not see these things, a lot of higher level things like group within an FS2 or queues or part join, they actually boil down to this under the hood. So even though you might not be using those directly, you are probably, if you use FS2 at all or Casafet at all, you probably are using them in your code. You just don't see them. This is just a foundation, so low level, but you can build on top of this to do everything you want. Cool. Feel free to come and talk to me after if you're scared to ask a question on the stage. I'm not on Twitter, obviously, so come and talk to me on GitHub. My talks and slides and everything are on my blog, and I have some example code for the cached thing. And thank you again. It's been a great conference. So thank you guys for inviting me, and thank you all for being here.
Fabio. Thank you so much.
Yeah.